Hi everyone, welcome to this past marathon, Modernizing Your Data Platform. We are excited you could join us today for Ken LeTourneau and Alessandro Goncalves session, SQL Server 2008 End of Support is Coming, Modernizing with Intel Technologies Part 2. This past marathon features back-to-back live webinars delivered by expert speakers from the PAS community. The sessions will be recorded and posted online after the event. You will receive an email letting you know when the recordings are available. My name is Indira Bandari and I will be the moderator for this session today. I have a few introductory slides before I hand over the reins to Ken and Alessandro. Moving on to the next slide. Next slide, Ken. If you require technical assistance, please type your request into the question pane located on the right side of your screen and someone will assist you. This question pane is also where you may ask any questions throughout the presentation. Feel free to enter your questions at any time, and once we get to the Q&A portion of the session, I'll read your questions aloud to Ken and Alessandro. You are able to zoom in on the presentation content by using the zoom button located at the top of the presentation window. Please note that there will be a short evaluation at the end of the session, which will pop up after the webinar ends in your web browser. Your feedback is really important to us for future events, so please take a moment to complete this. Moving on to the next slide. In the lead up to SQL Server 2008 end of support, we have recruited Sandy, an expert in all things migration, along with an all-star lineup of speakers from Microsoft and Intel to smoothly guide you to your final destination, a modern data platform. Whether you are interested in moving to an updated on-premises, cloud, or hybrid solution, PAS, Microsoft, Intel, and Sandy, of course, have teamed up for a must-attend series of webinars, in-person events, and migration resources dedicated to giving you the tools you need to migrate with confidence. Visit pas.org/modernization to see the collection of on-demand videos, helpful blogs, presentation slides, and other industry-leading learning content from PAS, Microsoft, and Intel. Moving on to the next slide. This PAS marathon session is presented by Ken and Alessandro. Ken has been with Intel for 20 years and is a solution architect focused on big data and artificial intelligence. He provides a unique perspective to leading IT decision makers on why AI is important for the 21st century organizations. Ken works with leading software vendors on architectures and capability for big data solutions with a focus on analytics. Moving on to the next slide. Alessandro is responsible for performance proof points and solution architect for Optane SSD on Microsoft platform with over 20 years of experience. And without further ado, here is Ken and Alessandro with SQL Server 2008 EOS is Coming, Modernize with Intel Technologies Part 2.
All right, thank you very much, Indira, and welcome everyone. Okay, just a quick overview of our agenda for today. We're going to go over the kind of the following topics here. We'll give a primer on what is Intel Optane Technology. We'll get a little bit deeper dive into what is persistent memory. We'll take a little bit a look at the Intel Optane DC persistent memory usage modes, of which there are multiple. We'll describe how that's a little bit different than Intel Optane data center SSDs. And we're going to take a look at Microsoft SQL Server and use cases for Intel Optane Technology. So how could you actually apply these products or technologies to your SQL Server environments? And lastly, for folks that are curious about how to get started or some handy reference designs, we'll do a brief overview of what Intel Select Solutions for Microsoft SQL Server looks like. Okay, so what is Intel Optane Technology? Alessandro, did you want to take an answer at that?
Thanks, Ken. Well, Optane Technology is just a union between a revolutionary 3D cross-point media within Intel IPs that comes to our Intel Optane technology, whether it's a SSD or a memory DIMM that we are going to talk about it. So it is a foundation on the 3D crosspoint with Intel system and hardware and software. So that's what makes unique from regular SSDs or regular DRAM that we have available today.
Right. And available for two products in the data center, the solid state drives or these new Intel Optane DC persistent memory modules. Okay. All right, so let's talk a little about this construct we call kind of the memory storage pyramid. You can see this is kind of color-coded from working the bottom of the triangle to the top, from blue to red. And that's really meant to illustrate kind of the warmness, if you will, of the data. You want to have an efficient way of storing your data such that, cost optimized and kind of access patterns optimized. So you want your colder data can afford to be on slower storage, and by slower I mean lower latency, longer retrieval times, because you don't operate it on it as frequently. And as you work up this pyramid, your data starts to get a little bit warmer, so you want to match up your storage architecture to those access patterns. So we have this, newly launched kind of Intel 3D NAND SSDs using 4 bits per cell or QLC technology, kind of an efficient storage there. You walk up a little bit more of that pyramid into more traditional NVMe SSDs or non-volatile memory express. And as you're getting closer and closer to DRAM, we now have slotted in these products Intel Optane DC solid state drives, which is, Alessandro mentioned, take that 3D crosspoint technology. They put it on the PCIe bus in a traditional solid state drive form factor. And then filling in that last gap before you get to DRAM, improving memory capacity with persistent memory, is Intel Optane DC persistent memory. Again, takes that same 3D crosspoint media, puts it into a memory module that sits on the memory bus, and kind of bridges that latency gap between the PCIe bus and DRAM. Okay, so I mentioned this on the last slide. You have a goal of this building an efficient data-centric architecture based on access patterns. So when data is acquired or generated, it has kind of a lifespan, and it's typically considered hot when it's first created. It needs to be analyzed right away or persisted right away. And as it ages, it tends to get cold. You don't access it quite as frequently. So you're able to distribute your hot data and your cooler data to appropriate storage mediums. And so kind of building out that pyramid again, we can show our cooler data, it makes sense to put it on hard disk drives or very cost-efficient SSDs. And as it starts to warm up, you want to put on some more performance-optimized SSDs. But again, there's still that gap up until you get to DRAM where your hottest data sits. And so on the right, we've kind of built out this logarithmic scale that kind of shows, as you walk up this pyramid, here's your kind of capacity characteristics and your latency characteristics for those types of storage. So when you're in hard disk drive or tape and you're cold tier, you can be looking at tens of terabytes of relatively cost, I won't say cheap, but very, cost-efficient storage, but the access times, into the hundreds of milliseconds. As you start to walk up to SSDs, you're still in the tens of terabytes of capacity. You get your access time reduced to hundreds of microseconds, so, kind of a 1,000-fold, decrease, if you will, there. But then there's this big jump. As you go from SSDs to DRAM, you lose these terabytes of capacity, you go down to tens of gigabytes, but your access times are now in the nanoseconds as opposed to microseconds. And as you get ultimately up the top of that pyramid, you're on the CPU, where you're talking picoseconds or nanoseconds, but you're talking megabytes or kilobytes of cache. So if we can insert these Intel Optane technology based products, again, the solid state drives and the persistent memory modules. And you can see with the solid state drives, we're still into the kind of terabytes of capacities. We're now down to sub 10 microsecond access times by virtue of being on the PCIe bus coupled with this 3D crosspoint media. But there's still a bit of a gap between that and DRAM. And that's where we think Optane DC persistent memory is a good fit. You're now in kind of the hundreds of gigabytes, so you're denser than DRAM, and your access times are now sub microsecond. So it kind of completes the picture. All right, so focusing on Intel Optane DC persistent memory, which was launched in April of this year, it's coming to market again, and it's DDR4 kind of pin compatible, requires an Intel 2nd Gen Scalable processor-based system. Comes initially in three capacities: 128 gig, 256 gigabyte, and 512 gigabyte. And again, if you notice, that's bigger than what DDR4 can do today. Does support encryption out of the gate. It's been optimized for 5-year warranty for all the write patterns someone might throw at it. And when we say it's big and affordable, it's because it's larger capacity points than DRAM, and we expect it to trend on kind of a cost per gig basis to be more affordable than DRAM. So it gives us high performance storage. Again, it's persistent, unlike DRAM, which is volatile, which loses all the data on it on reboots. So we like to say you kind of get the best of both worlds with Intel Optane DC persistent memory. It has memory attributes, and that it's comparable performance to DRAM. It's got storage attributes, and that hey, it's persistent, like the name implies, and comes in higher capacity points than DRAM DDR4 offers today. So that's Intel Optane DC persistent memory. We also have Intel Optane solid state drives. Again, so this is a SSD form factor. Using that same 3D crosspoint media, offers low latency as well. So it is also a high performance storage device of its own. And similarly, a lot of those characteristics that relate to the storage attributes, the high endurance, the encryption, they're present in this product as well. Alessandro, is anything else you'd like to mention on the solid state drive piece of this?
Yeah, and also since being an Optane technology, but it does not have any compatibility issue with, not issues, but compatibility with the legacy Intel CPU. So you can take advantage of our DC P4800X on SSD form factor for our legacy Xeon platform.
Yeah, that's a great point. That's a great point. It is an NVMe device at its core, and that ecosystem has been around for a number of years now.
Yep, and that's really interesting on that point, and that enables us to differentiate between the DC persistent memory and DC SSD form factor.
Yes, exactly. We'll get into some use cases for that specific to SQL. I'm going to hand it to you to talk a little bit more of what is persistent memory, okay?
Sure. Thanks, Ken. So in order to talk about persistent memory, I'd like to do a little definition on terms, because that's something you're going to start hearing more and more from now on, as soon as the technology starts being more popular with the second generation Xeon and the DC persistent memory Optane. The first one would be DAX, which is basically direct access. So when you use Optane persistent memory and want to present a bit addressable space to your applications, you're going to go to a DAX mode or a DAX file system. So this is basically direct access, meaning that you can have a bit addressable space. The other one would be CLWB, or cache line write back. Basically, this is internal to the CPU, that meaning that you are flushing your cache lines from the CPU to the memory controller. So that what enables you to have the persistency go from just visualizing the data that is available to you, and tell the CPU to flush its cache lines to the persistent memory portion. So that will go to your memory controller. So from the flushing, it goes to a queue called the WP queue, which is write pending queue. This is where on the portion of your stack where we are already power protected. So in the case of a power loss, once the information is flushed from the CPU cache lines into the memory controller within this queue, your data is safe. So it will sustain power loss. Other point is the PMDK. Basically, it's an Intel-sponsored open library where you use to make your applications persistent memory aware, where you have enhancements on how to deal with flushes and how to make your application use the persistent memory part. So when we talk about flushes, you're going to hear lots of different ways that we can command a flush. So every time you do a msync on Linux or on Windows or flush file buffer, you're just telling to flush your memory contents. In this case, that might be very costly in performance. So with PMDK, you have a more flexible way and a different way to issue those flush commands that will have a more performance to your application. So, and we call also a second one deep flush, where you have a point where you clean up all your cache lines. So there will be different ways to do what we call load and store from memory. So that you're moving away to a file system or a file semantics to a load store semantics. Let's next slide. So when we talk about DAX, this is how we envision the structure of DAX, where your application will have two main paths to access your persistent memory media. Either you're going to go to a PM-aware file system. In this case, on Windows, will be NTFS. On Linux, or XFS or ext4. Mounted as a DAX file system. So even though you're going to have a PM device, you have to tell the file system that you want to mount as a direct access or DAX. The good thing is both Windows and Linux call DAX. Or when you have your application completely PM aware, either you change your code or you introduce PMDK, you can technically bypass your file system, and from your application, you're going to control the load store semantics. So there will be two ways to use a DAX mode. And if you see on the left-hand side, you see block mode application, which is basically you're still using the old standard file APIs. You could still use a persistent memory device, but you're not going to have any memory mapped region to use. So you're going to go through your regular IO stack, like we're going to see on the next slide. So talking about IO stack, like I mentioned, you could still use your SCM or your storage class memory, either Optane DC persistent memory or any NVDIMM device. They will use the same driver within the operating system. But you see the big difference from left to right, where you have your traditional IO stack, where you go from your volume manager, your disk, your store port, your mini port, and you access your media. On the middle, where we call storage over app direct, basically is we are presenting a regular file system that is mounted on a persistent memory device. You still have some parts of the stack. So from left to right, you're increasing your performance, but you still have a overhead on the IO stack. And for the right, you have the app direct mode, where we mount a DAX-aware file system, or you have your application directly access the memory contents of that device. So you have a mapped memory access to. So the further to the right, you have more performance. When we talk about performance, we have lots of other attributes on the application that will give you more or less performance. You have a different behavior, but on overall, that's what we need to understand. If you're using storage over app direct, you still have a overhead over the IO stack. You still have a volume and partition manager, but going to a app direct mode, and we're going to talk about those different modes, you are decreasing the amount of hops or layers to access the medium. So basically, that's what I wanted to show. Next slide. So now we're going to talk about the Intel Optane DC persistent memory use modes. So you already heard me talk about app direct and storage over app direct, and you have memory mode as well. So we're going to show the flexibility of having Optane DC persistent memory on your system, where you can choose the best way to utilize that media. So you're not going to be bound for only one use. You can change or choose the best use case for you. So let's go ahead and talk about the first one. So the first one is what we call memory mode. As the name entitles, is we present Optane DC persistent memory as memory, regular memory to the operating system. So we're going to have a mix of regular DRAM DIMMs and DC persistent memory on your system. And your DRAM is going to be used as a near memory or as a cache. So this mode is not persistent, so it will wipe out the contents of the memory every time you power cycle. So, and that's one point that we always need to remember in this case. Ken has worked with that. Any other comments on the memory mode? So I guess we're going to see some testing that we did on our Cascade Lake launch. But basically, we need to remember that your DRAM is a near memory acting as a cache. The memory controller will try to keep your hot data in DRAM and your cold data within your DC persistent memory. Really good applications for in-memory database, large working sets. We always need to understand our applications needs regarding throughput and the amount of writes that we do, because that will give you a different experience for each application. Let's go for the next slide. So the next mode, that's what we call app direct mode. So this is the one that we present Optane persistent memory as a persistent memory, as the name says, and we're going to use the storage class memory driver within Windows or Linux. So the great idea in this point is applications that can use app direct will have to either be changed with Intel PMDK or being changed within their code. So you need to be sure that your software can support the memory mapped semantics that we are introducing in this point. It's fairly fast because it's in-place persistence. So when you're just changing memory on the fly, so there's no paging, no context switching, no interrupts, no kernel code will be executed. So the real performance comes to that idea that we're now moving data from a memory structure to a persistent structure on a SSD, on a HDD. You're definitely just doing load and store on the memory itself. But we need to understand that the flush that we call on the, if you look at the diagram on the right-hand side, is you have memory, you have data on your cache lines on your CPU. Once you do your flush, that content is going to go to your memory controller. And that's where we are actually protected from any power fail. And also, we need to remember that with persistent memory, you could do RDMA. Mainly, you could access that memory mapping from one system to another. So, like we do with RDMA networking, we could do the same thing with your application. So, the PMDK does support the remote memory access. The other mode for AppDirect, that's what we call storage over AppDirect. Basically, we're presenting the device as a traditional block device. So we're going to use a standard file system API, raw access. So from an application standpoint, it will behave as if it is a regular block device. So you have the same points where you have a file system, you have a volume manager, and there is no change on your application. So from the modes that we have, on memory mode, as long as the hardware and the operating system supports the memory mode part, your application does not need to change because it is regular memory as far as application. On storage over AppDirect, the same point. If you have a hardware that does support and as your operating system supports, you are going to have the same issue or the same behavior. So on those 2 points, you don't need to change your application. So let's talk about Microsoft Server and the Intel Optane Technology. Hello, Ken. Would you like to take over for the Microsoft Server and Optane Technology? Well, I think Ken might have a.
Thank you.
All right.
Again. Yeah.
All right.
Okay, sure thing. Thanks, Alessandro.
Thank you, Ken.
Okay. Yeah, so what will be some of the goals of applying Intel Optane technology to Microsoft SQL Server? Both, acceleration and maximizing your investment in your environment. We have to take a look, though, when we do that, there's some software and hardware dependencies, if you will. So we're going to walk through just a few different configurations and use cases or applications of Intel technology. So let's start with the Intel Optane DC SSD. We have this bullet point as legacy hardware. I don't know if I would consider it necessarily legacy. I would just say it's, pre-Intel 2nd Gen Xeon Scalable. That could be anything from, a year old to 3 or 4 years old now at this point. This does offer, it's a fast block storage device. And when we say non-enlightened here, that's actually a Microsoft term for supporting full-blown AppDirect within SQL Server itself. It can also be used as a regular buffer pool extension device. Let's look at some more of those general use cases. So if there was no application or no need for persistent memory support, you consider using an Intel Optane solid-state drive. Again, this is fast storage on your quote-unquote legacy hardware. You can tier it in here, right? So you may have it as a good home or a good use case might be, I'm going to put my regular database files, my MDFs, SQL Server logs and such, or SQL Server, not transaction logs, other logs, other SQL Server related files onto regular SSDs. But I might consider putting my transaction logs or my TempDB log or maybe TempDB itself onto an Intel Optane SSD, which is going to offer, better real world IOPS and performance over a NAND-based SSD with better latency characteristics as well. And again, to underscore Alessandro's point there, you don't need a 2nd Gen Intel Xeon Scalable platform-based system to leverage Intel Optane SSDs. Okay, so now we have a situation where we have hardware that supports persistent memory, but we have application software that does not support it. So now we can use it as we can use Intel Optane DC persistent memory as fast storage and potentially as system memory. And that's what we're trying to illustrate on the left there. So that would be both memory mode and storage over app direct mode. Specific to SQL, you have an operating system that's got to support SCM, which would be Windows 16 moving forward, but a SQL Server version that doesn't support persistent memory, which one feature excluded, that's going to be SQL 19 and forward. So there's kind of limited support in SQL 16 and 17. So one option here would be to use Intel Optane DC persistent memory as additional memory on the system, or it could be used as that fast block storage. And we didn't actually touch on this, but you can actually operate in both modes at the same time with the product. You're able to partition it out anywhere as 0% memory to 100% memory, and kind of any point in between to allow you to actually do both on the same devices. All right, so I wanted to touch on one example of memory mode being used, and this is in a virtualized SQL Server environment. So this is a Hyper-V-based solution with direct attached storage. And what we did is we took basically two identical systems except for the memory components. So CPUs are the same, storage is the same, network is the same, software versions are the same. And we built an all DRAM configuration with 3/4 TB of memory. And one of our customers was able to share with us one of their database as a service workloads, if you will. We call them Cloud OLTP benchmark. And it runs simultaneous SQL workloads on the virtual machines installed in the environment and watches them to see if they're performing within a certain SLA. And that SLA is something like 95% of the queries being executed have to finish in a certain number of milliseconds. And so on that all DRAM configuration baseline, we're able to scale to 22 virtual machines running SQL Server that are able to perform within SLA. As soon as you go to 23, we're out of memory and we're out of SLA as a result. Now take that same configuration, take some of the DRAM out, just leaving 192 GB of DRAM as your near memory, and then put in 1 TB of Intel Optane DC persistent memory, and you're able to present a terabyte of usable memory or system memory to the hypervisor. And so that 33% bump in memory actually got us to 30 VMs versus 22. So a 36% increase in VM density running at the same SLA. Another way to spin that would be, given that it's almost an identical system cost to make that change. I mentioned kind of pricing earlier, where we're expect Intel Optane DC persistent memory to fall to be cheaper on a per gigabyte basis as in DRAM. So we're actually able to get to a lower cost, up to 30% lower cost, hardware cost per virtual machine in that environment as well. Okay, this concept of what we're calling reduced persistent memory support, tail of the log, and that has a much more verbose name from Microsoft. Persisted log buffer, I believe, is the term.
Yeah. Mm-hmm.
Yeah. But it was a feature new to SQL Server 2016 that allowed you to put what's called the tail of your transaction log onto an NVDIMM device, which allowed you to actually faster transactional throughput because just of the right characteristics of that device, it's persisted. You don't have to worry about flushing it later, so you can actually recover if there's an issue. And so you could actually run, and we did call it out on this slide, you could use Intel Optane DC persistent memory as both fast storage for housing the tail of the log or that persisted log buffer, and memory mode on the system to give you a bigger working set footprint. And then again, you can still tie in if you need them for TempDB or transaction logs. The rest of them, you can still use an Intel Optane DC SSD. You can still use a regular, let's say run-the-mill data center SSDs, but non-Optane based SSDs for the rest of your database storage. Okay, Alessandro, I'll let you take the example of expanding the buffer pool with persistent memory.
No, sure, sure can. So in this example for SQL 2019, there is a new feature for buffer pool, which is hybrid buffer pool. Basically, it uses the persistent memory as the extension of the SQL Server buffer pool. So our I/O and clean pages are stored on a pman space. So the point is you can, again, we add everything as AppDirect, but not necessarily. You can choose how much of your persistent memory will be used as buffer pool, and the rest could be either used as storage or more memory. But in this case, you're not extending the whole operating system memory addressable, but just the SQL Server buffer pool. So this is a example where you can use AppDirect mode with, for instance, SQL Server 2019 on Windows platform, which still does not support the full AppDirect mode, was as Microsoft called Enlightened mode. But on SQL 2019 on Windows, you could have it used as HBP and test it and extend the buffer pool for the SQL Server process.
All right, and so last but not least, that brings us to the enlightened version, or what we're calling all DAX for all. So as alluded to earlier, SQL Server 2019 is going to have support for full enlightenment with Linux being the lead platform. So that means you can place every type of database file onto one of these DAX volumes, turn on a particular trace flag, and then SQL Server will interact with those DAX volumes directly, rather than having to use any bit of the storage stack that we illustrated earlier. So in this case, you could think of it as primarily as fast storage. You've got this DAX volume hanging right off the processor that's built out of those Intel Optane DC persistent memory modules. And then you could still have, if you have additional data needs for backups or different databases, you could mix and match here. Put your mission critical stuff on the most performant, or ones that have a higher demand for performance on one solution versus the other. And I think we have a quick video to show on this. So for part of our launch event for Intel Optane DC persistent memory, we co-engineered a demonstration with Lenovo using their current 8-socket platform based on 2nd Gen Intel Xeon Scalable and their last generation 8-socket platform. And what we wanted to show was that by putting all of the 30 terabyte data warehouse onto the memory bus, or onto these Intel Optane DC persistent memory modules, if you will, what kind of benefit could we get from that, along with the new version of SQL Server that's optimized for persistent memory, and along with just some generational hardware gains as well. So let me go ahead and start this. I'm guessing a good chunk of the audience is probably familiar with a benchmark tool called HammerDB. And so what we did is we created this 30 terabyte data warehouse. We used clustered column store indexes, so it actually didn't take up that much space. It didn't take a full 30 terabytes, I should say. It still took 15 or 16. We were able to fit it into Intel Optane DC persistent memory. And then we ran some of the queries you normally see in a decision support type workload. And what we were able to show for some of these queries, and we're just illustrating a few of them here, was that we could get a 56% reduction in runtime, which corresponds to, if you kind of invert that, 129% increase in query throughput. So I think this story is going to get even better. We're still at the time we tested this on Windows Server 19. I think if we had done this on Linux at the time, or we do this again on Linux, we'll avoid another memory copy of the data, because again, we have that full enlightenment support. So it's just kind of a preview of good things to come in the SQL Server space with optimizations for Intel Optane DC persistent memory. Okay, so I'm going to take just a quick second here to talk about Intel Select Solutions. If anyone's looking for kind of just some building blocks, what is Intel Select Solutions? There are some predefined solutions for some popular ISV solution stacks, and they come from a range of different partners. The idea is able to just increase time to deployment, have a kind of a known and validated configuration for certain workloads, take some of the guesswork out of your procurement strategy, and then just kind of a broad hardware and software ecosystem in terms of support. Now in the SQL Server space, if you wanted to get started on something, as you're going down this migration path with SQL Server 2008 happening, we have our family we call V2 solutions. V2 is aligned to 2nd Gen Intel Xeon Scalable. We've got, one as part of our announcement, we've come up with a design that we feel is designed for kind of a multi-tenant database as a service environment. So building blocks for something like that. We call that Intel Select Solutions for Microsoft SQL Server on Windows Server. At the same time, we're engineering kind of that same strategy for Linux. And we're hoping in the second half of the year to come out with something that's optimized actually for orchestrated, containerized SQL Server, if you will. So you go kind of from DBAS more to SQL Server as a service, if you will. This is a bit of a departure from what we do with our V1 solutions, but there's still people doing, you know, our V2 are meant to be kind of general purpose hosting, range of workloads, multiple workloads, multi-tenant. Our first family solutions were designed for going after very specific workloads. So this concept of Intel Select Solutions for Microsoft SQL Server Business Operations versus Enterprise Data Warehouse. And as those names imply, the former was optimized for highly transactional or LTP workloads, and the Enterprise Data Warehouse was optimized, we would kind of say, for hybrid transactional analytical processing. And we did versions of that for both Windows Server and for Linux. All right, so kind of key takeaways here. We covered Intel Optane Technology and kind of both products. Tried to show that's got applicability for SQL Server, both bare metal environments and virtualized environments. We understand that there's both out there, and they're both virtualized is arguably probably a little more popular. We talked about they can both be used as block devices. In that case, and just standard file systems sitting on top of them, and that'll pivot on what kind of hardware we're talking about or what kind of software we're talking about in terms of being enablement or readiness. Which kind of dovetails into the third bullet there. Software enablement beyond having second Gen Intel Xeon Scalable platform is the key to take full advantage of persistent memory. Specifically, that's that app direct mode we were talking about, or in enlightenment within SQL Server. And then review the use cases here, which is most compelling or important to you, and maybe try and kick the tires on it. Do I need more memory? Can I leverage persistent memory? Or do I need all-out performance in terms of fast storage, whether that be over a persistent memory device? Again, that DAX app direct mode, or fast storage over a block device where I still have a little bit of a software overhead, but that might be just a nature of the OS environment that I'm running in. So Alessandro, any comments you want to make on that?
Yeah, I think for memory mode, just to be clear, Windows 2019 will support the memory mode portion. So from 2019 on. Talk about software enablement. So it will be using the latest and greatest kernel builds and file system builds as well. So if our next guest speaker, Bob Ward, has a great blog on the Linux file system versions where he put some enhancements there. So while we are testing and using, being aware of updates on kernel firmware for persistent memory and software versions, it will be key to take advantage on that. And faster storage over persistent memory device. It will give you, if you're using storage over app direct, is a regular file system though, so you won't have the option to mount as a DAX. So in order to use a DAX file system, it needs to be on full app direct mode on persistent memory devices. Otherwise, we're just using. And while you using DAX file system, you have to be aware that by reducing the I/O stack, you are removing hooks for mini filter drives. So think about deduplication, compression, antivirus,
availability group replication.
Yeah, all those things need to be thought out, because by reducing the I/O stack, the old way of treating data with mini filter drives will change as well. So your third-party vendors will need to catch up as well. So we need to make sure we pay attention to all those things as well. So I think we are about on the top of the hour, quarter one
we're
after.
right,
Yeah, and then
right
we
where we
can.
need to be. Yeah.
Yeah, and then can open for questions.
Okay, so we have a few questions. One of the questions from Glenn Berry is refs a PM-aware file system?
Is
Okay.
REFS PMM-aware file
RFS,
system?
yes. Yes.
No, just for now, it's just NTFS on Windows.
Okay. And another question from Glenn is, what are your recommendations for the DRAM and PMEM ratio for memory mode for SQL Server usage?
All right, so it's a little bit workload dependent. I hate giving the engineer answer that it depends. But if you're highly transactional, I think a good starting baseline is 8-to-1 Optane DC persistent memory to DRAM. If I'm doing a data warehouse type environment, I think that good starting baseline is closer to 4-to-1. It just kind of comes down to how much memory bandwidth the workload really needs, and whether or not it's operating most of the time in that near memory cache or not. So in the case of the latter or data warehouse type workloads, they tend to be larger working sets, and as you spill out of that, you do want a little bit more memory bandwidth. And the way to get more bandwidth is more devices. So that's why you see the ratio kind of come down from 8-to-1 to 4-to-1. Yeah.
Yeah. So one thing that we didn't mention on the slides, but there is a lot of permutations on how you populate your memory channels. So the more, like Ken said, the more devices you have, the more bandwidth you're going to get. So the ratios are important, like 4-to-1, 8-to-1, but also the amount of devices. So sometimes if you can populate more channels, you're going to have a greater bandwidth on the memory. So it gets a little bit more challenging on how to get the perfect solution on that.
It's not too dissimilar from, I would even say, solid state drives and RAID groups, right? You get more performance out of 2 smaller drives than 1 drive of the same combined capacity. You can think of that applying to Intel Optane DC persistent memory as well. You get more bandwidth out of 428 gigabyte modules than 1 512 gigabyte module.
Yeah, and the same as regular DIMMs. So you have 32 gigabyte DIMMs or 64 gigabyte DIMMs. So we have,
the interleaving practices would still apply. Yeah.
Yep.
Okay, another one question from Osvaldo D'Souza. In a same server, can you mix regular RAM with Optane persistent memory?
You actually don't have a choice.
Yes, you have to have it.
Yeah.
You have to have a mix. Okay, yeah.
Yeah, so it goes any channel that you want to put Intel Optane DC persistent memory on. You can put one of those modules in one of the slots, but it has to be paired with DRAM in the other slot. Now the reverse is not true. You can have channels with DRAM only, but any channel that's going to have Intel Optane DC persistent memory also has to have DRAM on it.
Okay. Another question from Osvaldo is, what is the normal lifetime for Optane persistent memory?
So they are warranted for 5 years. We didn't have it in this deck, but we do have some models projecting petabytes written over the lifetime of the device over that 5 years. Kind of varied on whether it's 100% write workload or a mixed workload. But as far as Intel standing behind it, it's meant to have a serviceable life of at least 5 years.
Okay, yeah. So far, those are the questions. Any other questions, please put them in the question pane.
Yeah, I guess the good takeaway is to understand the relation between hardware and software. As with new technology that brings some challenges on find the right way to transition to take advantage of the big working set that we're going to have with memory mode. Again, we need to understand your workload. So how much bandwidth you need. Sometimes we don't think about it, but data injection, for instance, that's a big concern. So how much throughput you actually need. So that will change on the DEX mode. Understand that we're going to be changing a memory view, and that change will be readily available, but not necessarily persistent. So visibility is not persistency when you're coding for persistent memory, because you have a memory map file, you change that data, but that data is not automatically persistent until you flush from your CPU cache to the persistent memory device. Some key takeaways that we have seen during testing.
Yeah,
but as long as
comment.
Yeah, go ahead, Ken.
I was going to say too, we're kind of at a software inflection point with this Server 2008 end of support. So it's really a good time to kind of take stock of your holistic environment, if you will.
Yeah, and sometimes change the old ways of storage, for instance, taking more advantage of availability groups, direct attached storage, the flexibility that you can recognize which parts of your deployment needs fast storage, more memory, that you can achieve with the same device. So and you can mix and match. So one thing that we'd like to make it clear is that you're not bound to a single mode. So you can choose part of your capacity on DC persistent memory as full memory, so to be addressable by the operating system in any other application running, and some part to be work as storage, either storage over app direct or app direct mode. So you're not bound by a single mode on that sense. Right. We don't have any further questions.
I would second if anyone's sticking online for Bob Ward, he's worth listening to. So if you're not, consider sticking around to listen.
Yeah, I saw the PDFs from Bob that's available. It's containers and Linux. It's really nice. And like I mentioned, if you haven't seen Bob's blog about the Linux file system, what he found out, really, if you want to go a little bit deep on buffering and write through and how does that work, that's a great blog. And some difference between Windows and Linux, and once we set a flag for direct access mode, not on the DEX, but just regular storage.
We have a few more questions.
Nice.
Naveen Kanuganti is asking, with Intel Optane, would that make any difference to always on availability functionality? AG Group.
Yes. So with persistent memory part, the first node of your availability group will now have so let's think about your availability group. So you could have a persistent memory mode on your second availability server or your application partner, and we in full mode. But on your primary, you won't have the persistency memory. If you use just storage mode or Optane SSDs, that won't change a bit. So that's one thing that changes.
And what about replication?
So yeah, within the availability group, the replication itself will be the same. You're going to take advantage of a faster media, but as far as using persistent memory type of scenarios, like you have the limitation of NVD or persistent memory, your primary server won't be able to use today the persistent memory point.
Okay. Another question from Osvaldo is, all features will all features work in SQL, Windows, Linux, and containers?
So, like we said, right now the full features are based on Linux, SQL for Linux, so the enlightened mode.
Okay. Yeah.
On SQL based on Windows, you could use memory mode, and the app direct mode, you still cannot put your database files on Windows, but you still could use storage over app direct, or if you want to do the HBP, which is the hybrid buffer pool extension with Windows, it's a app direct mode usage today. That might change throughout the life of SQL, but as far as today, if you want to really use persistent memory, it would be on Linux-based SQL.
And that's with SQL 2019 at that, so it's still
2019 CTP. Yes, thanks, Ken.
Yeah. Yep.
Okay. And one more question from Glenn is, are there any performance differences between the different persistent memory sizes?
So the answer to that is actually yes, but it's because you can actually program for different power levels as well. I can't really get into the details of what that looks like in terms of bandwidth for a 128 versus a 256 versus a 512. I'm going to refer to them as more kind of subtle differences, more so than drastic differences. But again, you'd never really look at them from an individual device level, because when you're deploying these, there's going to be multiple of them in play. And then you start kind of looking at the aggregate performance, and then how that translates to your application perspective. I don't feel like I'm answering that one with too much due diligence or doing it justice. The analogy I like to use is that, like, you know, our family of NAND SSDs has some different performance characteristics based on capacities. That is also true of these Intel Optane DC persistent memory modules. But again, they're not. They're certainly they're within close deltas of each other. Is how I'd phrase it.
Okay.
Yeah, I'll be more worried about your overall throughput for the number of devices that you have, rather than the difference in performance between capacity size.
Yeah.
Okay, I think that's all, I guess, for the questions for today.
All right, so I think we might just have a couple of finished slides for the.
Eric?
Yep. Oh, that's Bob's coming up next. Okay.
Yep. So in a few minutes or 1 minute, I guess it's
just 1 minute. Yeah, just one
Yeah.
minute. I think Eric is going to close off. So